Hello viewers, myself Dr. Mahantesh K. Welcome you all to this pre-recorded online sessions on electromagnetic waves, module 3 class 4. In this video, we will be discussing about Ampere circuital law along with its applications for different types of current carrying conductors. So what is Ampere circuital law? Ampere circuital law states that the line integral of magnetic field intensity about any closed path is exactly equal to the direct current enclosed by that path. This law is very helpful to determine the magnetic field when current distribution is symmetrical. In the figure to your right, the integral of H about closed path A and B gives the total current I, while the integral over path C gives only that portion of the current that lies within the C. Symmetry suggests that H will be circular, constant valued at constant radius, and centered on the current axis. Choosing path A and integrating H around the circle, we get H dl is equal to 0 to 2 pi H phi rho d phi. So H phi rho is constant. We'll take it outside. H phi rho 0 to 2 pi d phi, which is equal to H phi 2 pi rho, which is equal to I. Therefore, H phi is equal to I by 2 pi rho, which is stated as before. So now application of a Gauss law to a coaxial transmission line. Consider a coaxial cable of inner solid conductor of radius A. Let B be the inner radius of outer conductor and C be the outer radius of the outer conductor. So there will be three different cases considering the Amperian loop between the conductors. So we'll obtain the relationship between the magnetic field intensity and current as H is equal to I by 2 pi rho when A less than R less than B. Whereas field within the inner conductor, current uniformly distributed inside the conductors, then H can be assumed circular everywhere. Therefore, HDL is equal to integral 0 to 2 pi H phi rho d phi. But now the current enclosed is I enclosed is equal to I rho square by A square. So that 2 pi rho H phi is equal to I rho square by A square. Finally, H phi is equal to I rho divided by 2 pi A square when rho less than A. Rho is radius of an Amperian path. So now let us assume the Amperian path outside the coaxial cylinders, that is rho greater than C. In this situation, HDL is equal to 0 when rho greater than C. So field outside the inside the outer conductor when when the Amperian path is between the radii B and C, we obtain the equation for magnetic field, which is in terms of difference between C square minus B square. H phi is equal to 1 over 2 pi rho C square minus rho square over C square minus B square when rho lies between B and C. Now, if we try to plot a magnetic field strength as a function of radius in the coaxial line, you could see there is an increase, the steep increase in magnetic field I by 2 pi A and then slowly decreases when rho is equal to 2a and rho is greater than b and rho is greater than c. The magnetic field intensity is 0. So if we try to find a magnetic field arising from a current sheet for a uniform plane current in y direction, we expect an field directed in x axis or x coordinate. Applying Ampere circuital law to the path, we obtain hx1l plus hx2 of minus l, or hx1 minus hx2 is equal to ky. So magnetic field arising from a current sheet is given by h is equal to half of ky when z is greater than 0 and h is equal to minus half of ky when z less than 0. Thank you for watching this video. Hope you have understood the concepts of Biot-Savart's law and Ampere circuital law and application of Ampere circuital law to coaxial cables and a concentric sphere. Thank you for watching this video once again.